All right, so now we're gonna do a different lab, but we're still gonna use the same orbiter. This time, instead of looking at mass and speed, we're gonna be looking at distance and speed. So our orbiter, again, this is tube represents our planet. The string is the orbital distance, which is what we're gonna be changing. So this is 40 centimeters, and then we're gonna do one at 30 centimeters and one at 20 centimeters. And then we have our moon, again, which is just the white foam ball.
All right, so what you're going to want to do is, again, find a stopwatch, open up your clock app on your iPad or use your phone, and put it to 0. Ms. Thompson has her orbit going. When I say start, I'm going to start your stopwatch. When I say stop, you're going to stop. Ready, set, start. 1, 2, 3, 4, 5, 6, 7, 8, 9, stop. All right, and now you have your time for 10 orbital periods. All right, so now looking at our data table for 8.2, distance and speed of an orbiting body. The length of the line that Ms. Thompson was using was 40 centimeters. And the time it took for 10 revolutions was what we got on our stopwatch. I got 4.46 seconds. You may have gotten something similar according to your own stopwatch. And I'm going to divide this number by 10. What this is going to give me is going to give me an orbital period of 0.446 seconds. So that's the length of time it took to make one revolution.
All right, so we've shortened the string of our orbit to 30 centimeters. So this is now 30 centimeters. And we just did that by taping it to the side. We haven't added any mass. So the only thing that we've changed is the length of the orbit.
All right, go ahead and reset your stopwatches to 0. All right, when I say start, you're going to start your stopwatch. When I say stop, you're going to stop. Ready, set, start. 1, 2, 3, 4, 5, 6, 7, 8, 9, stop. Okay, now you have your new time. All right, on trial 2, Ms. Thompson had a length of 30 centimeters, and the time it took for 10 revolutions is 3.95 seconds. And we're going to divide that by 10, and we get an answer of 0.395 seconds. So that's the length of time it took for one orbital period. All right, go ahead and reset your stopwatches to 0 seconds. When I say start, you're going to start. When I say stop, you're going to stop. Ready, set, start. 1, 2, 3, 4, 5, 6, 7, 8, 9, stop. And here's our new time. So, in our third trial, we've shortened the string length down to 20 centimeters. And the time it took to make 10 revolutions was 3.03 seconds. Divide that by 10, we get an answer of 0.303 seconds. So the length of time for the moon to orbit around once was 0.303 seconds. And what we see is a trend happening here. The time is decreasing. So that means the speed of the orbit is increasing. Think of this analogy. Think of a race car driver going around the track. The lower the time that race car driver has, that means the faster they're going around that track. So take a moment right now to answer this question on your own. How does the orbital period change as the sphere's distance from the handle decreases?
All right, so now we're going to take a look at actual data for Jupiter's 4 Galilean moons. And so these are in order from distance out from Jupiter. So Io is just over 400,000 kilometers from Jupiter. Europa is almost 700,000 kilometers from Jupiter. Ganymede is just over 1 million kilometers from Jupiter. And Callisto is 1.8 million, just over 1.8 million kilometers from Jupiter. So their distance is increasing from Jupiter. And the orbital period, the amount of time it takes them to go around Jupiter, increases. So Io orbits Jupiter in 2 days, Europa orbits Jupiter in 4 days, Ganymede orbits Jupiter in 7, and Callisto takes 17 days to go around Jupiter. So what I want you to do is take a minute and describe that relationship between the planet distance and the orbital period. All right, so we're going to graph that data from the previous table. So we're going to show moon distance versus orbital period. So moon distance is going to go on our x-axis, and orbital period is going to go on our y-axis. Now we need to set this up with appropriate distances. So what we're going to do is each one is going to be 1, but I can't fit all those in there and make it look neat. So I'm going to do 2, 4, 6, 8, 10, 12, 14, 16, 18, and 20. So this will be the same as 2 million kilometers away from Jupiter. That's what this times 10 to the 5th means. Now, we're going to do the same scale over here for the orbital period in days. So this is going to be 2, 4, 6, 8, whoops. This will be 10, 12, 14, 16, 18, and 20. So there's the scale set up for our graph.
All right, now we're going to plot Jupiter's 4 Galilean moons, starting with Io. Io is the closest one to Jupiter. It's at about 420,000 kilometers away from Jupiter, so about 4.2, right there. It has an orbital period of 2 days. So there's Io. And then the next moon is Europa. Europa has a distance of about 6.7, which is 671,000 kilometers away from Jupiter. And it has an orbital period of 4. So about right there, that's where Europa is. And then the next one is Ganymede. Ganymede is about 1 million kilometers away from Jupiter. And it has an orbital period of 7 days. And this is Ganymede. Then our last and 4th Galilean moon is Callisto. Callisto has a distance of about 1.8 million kilometers away, and it has an orbital period of 17 days. So there is Callisto.
All right, so what our data shows here and what we can clearly see in the graph is that as the moons get further and further away from Jupiter, the time it takes for them to orbit, the orbital period, increases. So more distance, longer time. So you might be thinking, well, of course, the time is going to increase as it gets further away because the distance is longer, Ms. Thompson. So if an object's traveling longer distance, it's going to take more time. But actually, here's some data on different bodies, planets, and moons. And so if we look at Jupiter's moons right here, we have Io, Europa, Ganymede, and Callisto. And there's the distance. But right here, orbital velocity, this tells us how fast something is moving. So we know that like 75 miles per hour is faster than 55 miles per hour. So right here for Io, you can see that its orbital velocity is 17.3 kilometers per second. So it's actually traveling faster than, say, Callisto, which is only traveling at 8.2 kilometers per second. So not only is the distance further, but this moon that's closer is moving a lot faster. And that's because it's closer to Jupiter and there's more gravitational pull, which is making that moon move